chapter 2, we introduced the main concepts of linear algebra, the whole vector space apparatus. In chapter 3, what we're going to talk about is how we can actually simplify some of the required computations, the types of things that we would like to be able to do, such as finding a basis for a vector space and finding the dimension of a vector space. Like we gave examples that were pretty simple examples because we didn't really have a routine or protocol to solve linear systems. We're going to remedy that situation in this chapter. It's a little bit more dry. It's much more technical. It's algorithmic. It is crucial that you practice solving linear systems. The main tool at our disposal is going to be something called Gaussian elimination or row reduction. It's not too difficult to do that. And in the real world, you would never do it by hand, right? You'd write code or you'd use software to do these things. But in this course, you have to do it by hand. And I remind you, you do not have access to a calculator. And so you need to practice this so that it becomes second nature, that you can do it without really thinking about what you're doing. We're going to talk about how we solve linear systems. Then we will talk about matrices. Matrices exist in their own right, but you can link to every linear system something called the augmented matrix of the system, and that's an object on which you can operate that is typically easier to work with than the linear system to start with. So we'll talk about this and how we can use these matrices to solve the systems we must solve. And then we'll talk about matrices also in their own rights, like the types of things you can do for matrices that don't necessarily exist only as an augmented matrix. We'll also do some applications once we have all the tools at our disposal. I want to remind you, very important thing here will be to understand Gauss-Jordan, Gaussian elimination, which we also call row reduction. We've encountered linear systems, right, when we were looking for intersections of planes in R3, for instance, or if we were trying to solve for a vector as a linear combination of other vectors, right? If we want to say, well, x, y, is that a linear combination of, these three vectors? And we would say like xy is equal to a times the first vector plus b times the second vector plus c times the third vector. And then we had to find a value of a, b, c that would give us this vector xy as a linear combination. They also arise if we want to check if a set of vectors is linearly independent or not. I'm not writing it down explicitly, but in many instances, they are going to be crucial when we want to write a subspace W as a span of a set of vectors we would like to be as small as possible, so linearly independent. That's part of the link here. In real-life applications, they very often occur, balancing chemical equations or solving these physical systems, trying to find the tension in a variety of ropes, or potentially as optimization constraints. They're pretty much everywhere. And it's not only because linear systems apply everywhere in the real world, although it often does apply in the real world, but it's also because as a first approximation of what's happening in the very complicated universe, they're like sophisticated enough to be able to give us something meaningful, but simple enough that we can easily work with them. So they're also a tool of convenience. If you study math and physics and chemistry a little bit more, potentially even economics and some of these other, let's call them softer disciplines, you will see that real-life models typically nonlinear. But it's hard to understand a nonlinear model properly. And so we often use the linear approximation as our first pass to understanding the system. That is not unlike, if you've studied calculus, the idea that if you have a curve, which could be very complicated, at a given point, if you look at the tangent line here, the linear approximation, well, it's a bad approximation far from that given point of tangency, but close to the point of tangency. Like if you just look at the small neighborhood here, the straight line approximation isn't that bad of an approximation to the full curve, which is potentially very non-linear. So linear systems, very, very, very commonly used. Sometimes they shouldn't be, but they're used because they're very convenient. It's important to know a little something about these systems. What's a linear system? Well, actually, it's a collection of linear equations. You have to have more than zero, so at least one linear equation. Let's say that we have m linear equations. By linear, what we mean is that when the variables appear, they appear alone to the first power. If you study regression analysis, you'll see something that, especially if you look at polynomial regression, you'll see something that looks like it shouldn't be linear because you have powers in it, but the powers are not the variables. The powers are the polynomials, x squared, x cubed. What we care about is the coefficients in front of those functions. These are the variables. So m linear equations and n variables. So you have m rows, typically you have n columns, together with a right-hand side, which takes you what value the linear equation takes. And you want to solve these simultaneously. A solution to such a linear system would be a set of values for all of the variables in your system that makes all of the equations hold simultaneously. So we're going to show you some of the concepts, or at least help define some of these concepts with a very simple system. We have a system of two equations, two rows, in four unknowns, x1, x2, x3, and x4. And it is traditional when you write those out and you know there's going to be, say, four unknowns, to leave an empty space if one of the variables is not represented in the equation. So typically the x1s go in the first column, x2 in the second column, x3s in the third, x4 the fourth column, and at the very end, right-hand side of these equal signs, we have what we call the constant terms. So this would be a system of two equations and four unknowns. I'm just going to say system because we're only ever working with linear systems in this course. But I should recall it a linear system of two equations and four unknowns. And typically you also name the unknowns, x1, x2, x3, x4. Four unknowns could also be x, y, z, w. Doesn't matter what you call them whatever you want. But the coefficients, of course, in front of them will be the same. And that's really the structure of the system, is all these coefficients. There's a 1 here, there's a 2, there's a 0, x cubed, x3 here, I should say. And then you can also view this as 0, x1 plus 0, x2 plus. That's the kind of stuff we're talking about. So you have the coefficients in front of the variables, the unknowns. We have the constant terms, and we have, well, as many equations as we need. The vector 1, 0, 0, 0, relative to the previous system that we just listed there, because that's a specific example of a system of two equations and four unknowns, is not a solution of the system, because if you replace x1 by 1, x2 by 2, x2 by 0, x3 by 0 and x4 by 0 per its solution, if you replace these values into the variables, into the system, then you're going to get that the second equation is not satisfied. Like, let's verify if this is indeed the case. 1, 0, 0, 0. So let's go back one slide. I'm going to replace x1 by 1, sure, x2 by 0, x3 by 0, x4 by 0, and I get 1 plus twice 0 plus 0 plus 0. Yeah, that for sure is 1. But if I replace the same 1, 0, 0, 0 in the second equation, then I get 0 minus 0, that's 0, and that's not equal to minus 1. So the two equations are not satisfied simultaneously, and so 1, 0, 0, 0 is not a solution to the system. On the other hand, 0, 0, 0, 1, x1, x2, x3, x4, that is a solution to the linear system, because on the one hand, 0 plus twice 0 plus 0 plus 1 is indeed equal to 1, and then 0 plus 0 plus 0 minus 1, yep, it's equal to minus 1. So the vector 0, 0, 0, 1 as a solution is a solution to the linear system. It satisfies both equations. Is it the only solution? Well, that's often a question of interest to us. When we do have a linear system, we want to know if it has a solution or not, and if it does have a solution, whether the solution is unique or whether it's not unique. And you remember, we've seen this before, right? This is something that could be interesting when we want to find out if a set of vectors is linearly independent or not. We try to solve the dependence equation. And if the dependence equation only has the unique trivial solution, then we know the vectors are linearly independent. And if it has more than one solution, then we know that the vectors are linearly dependent. So that's an interesting question. Like, how many solutions does a system have? The general solution would be a way to write all of the solutions simultaneously. Now, there's going to be a bit of a challenge here, because if we're talking about linear systems, there's only three possibilities. They either have no solution, or they have a unique solution, or they have infinitely many solutions. And it's not obvious how you would write down infinitely many solutions. Well, here's one way in which you could write this thing down. You write it as a set where on the left-hand side you have the structure of the solution, which will include or involve free parameters. And on the right, you have a list of the parameters that are free-ranging. So here, the general solution apparently, we'll have to verify that this is indeed the case, apparently consists of all the vectors in R4 of the form 1 minus 2s minus t, s, t minus 1, and t, where s and t are allowed to be any real number you want. We call them the free parameters. So there's infinitely many solutions, because s can take on infinitely many different values, so can t. And assuming the problem has been solved properly, what we would actually say here is that there is a doubly infinite general solution set, because it is described with the help of two crucial free-ranging parameters. This S, if it was a subspace, it's not a subspace though. You gotta be careful. You cannot write this as the span of two vectors because of the term minus 1 here and the term 1 here. And these terms appear because, I'll show you why later, because of the fact that the right-hand side is not a vector of zeros. The right-hand side contains non-zero values. We say of the system that it is not homogeneous. So the solution set is not a subspace. But if it was a subspace, you could write it as a span of two vectors. So the dimension would be 2. that solution is something akin to a plane. It's just not a plane through the origin. So we can't really talk about its dimension from a vector subspace point of view, but we can definitely talk about its dimension from a geometrical point of view. It's a plane in 4 space. So it has 2 geometric dimensions as opposed to 2 algebraic dimensions. How do we verify that this is indeed a solution? Well, there's 2 steps, right? The first thing we would have to check is that everything that is of this form is indeed a solution for the system of equations. That's easy. We literally replace 1 minus 2s minus t whenever we see x1, whenever we see x2, go with s, whenever you see x3, it's t minus 1, and whenever you see x4, give me a t. So let's do that. Let's replace x1 by 1 minus 2s minus t, x2 by s, x3 by t minus 1 here, and x4 by t. If you work it out, you'll see that the 2 s's cancel, the minus t and the t cancel, and you're left with 1 is equal to 1. So yeah, that first equation is satisfied with a solution that looks like this. And the second equation has x3 minus x4, t minus 1 minus t. The t's cancel out, you're left with minus 1. Yep, it is a solution. So everything of this form is a solution of the system, which is good, but we are not done. If we want to show that the general solution to the system looks like this, we have to show that nothing else really can be a solution. But if you do have a solution, it has to be in that general solution set S. So how are we going to do that? Well, we can use the first equation here to solve for x1. So basically, you go back to the first equation and you send everything which is in an x1 to the other side. So we have 1 minus 2x2 minus x4. When we send them to the other side, we send them by subtracting them on both sides. If that's the case, then you can do something like this with the second equation. We'll solve for x3, say. So we had a minus x4, we'll send it to the other side, and that gives us minus 1 plus x4. So x1, x2, x3, x4, if it is going to be a solution of the system, it absolutely must be that as a vector, you can write it as 1 minus 2x2 minus x4, x2, minus 1 plus x4 and x4. And now all you have to do is to change the name of x2 to s and x4 to t, and you recognize that this thing has exactly the form required to be in S. So we showed that everything that was in S was a solution of the 2 equations. That's great. And we show that if something is a solution because it satisfies both of the equations, we can rewrite these equations in the format that makes it clear that the solution belongs to S. So the general solution is indeed the set of all vectors that satisfy this condition that you can write in this form. In such a solution, S and T are the parameters or the free parameters of the general solution. Because the solution set S has parameters, then you have automatically infinitely many solutions if it's a true linear system. Because every different value of S and T gives a different solution. Now, when I say that S and T can take on any value, I don't just mean that they have to be integers. S could be minus 1/2 and T could be pi. These are acceptable choices. They'll give you a solution. We'll do a few more examples here to sort of get a sense for what general solutions are possible. And also, this is very important because good mathematicians are lazy mathematicians. Also, for what type of system is easier to solve, because we're going to try to transform our systems into easy to solve systems. so we don't have to think too hard about how to obtain the solution. Here's a 3 by 3 system. 3 by 3, I remind you, means 3 equations, 3 unknowns. The unknowns are x1, x2, x3. The 3 equations are, well, as they're written here, and there's a constant vector, constant terms on the right, 4, 5, and 1. Each of these represents a plane in R3. x1 plus 2, x2 plus 3, x3 is equal to 4, that's a plane. x2 plus x3 is equal to 5, also a plane. x3 is equal to 1. So when you try to solve this system, you're trying to find the intersection of 3 planes. Turns out that the system in question has only one solution, the solution -7, 4, and 1. How do we verify this? Well, I don't have a choice here. x3 has to be equal to 1 because that's what the third equation gives me. Okay, so x3 has to be equal to 1. So I can replace every value of x3 by 1. So I have x2 plus 1 is equal to 5. Or if you want, x2 is equal to 5 minus 1. So x2 has to be equal to 4. So now replace all the x2's by 4. And I'm left with x1 plus 2 times 4 plus 8 plus 3. So x1 plus 11 is equal to 4. The only value that satisfies this would be x1, which is -7. 7 plus 11 is equal to 4. And we see that there cannot be any other possibilities. Here now we have a 2 by 2 system. X plus y equals 1 and 2x plus 2y equals 1. I claim that it has no solution. Perhaps you could say that the general solution is the empty set. No vector in S could ever solve this. Why? Well, view it this way. On the one hand, you need to have that x plus y is equal to 1. On the other hand, the second equation, you have to have that 2 times x plus y is equal to 1. Or, if you'd rather, that x plus y is equal to 1/2. So, simultaneously, x plus y should be equal to 1 and x plus y should be equal to 1/2. But it's impossible for the same number, x plus y, because that's a number, to both be equal to 1 and to 1/2. So there's no solution. When a linear system has no solution, we say that it is inconsistent. The equations are not consistent with one another. If the linear system has at least one equation, then we say that the system is consistent. When you set up the dependence relation to demonstrate linear independence, your corresponding linear system is consistent because it always has at least a trivial solution, the solution where all the variables take on the value 0. Here's an example of a system which is consistent. It turns out it doesn't have just one solution, but we don't care about this right now. It has at least one solution, right? x1 plus x2 minus x3 is equal to 0 is the first equation. 2x1 minus x2 plus x3 is equal to 0. And the vector 0, 0, 0. So if I replace x1 by 0, x2 by 0, and x3 by 0, I'm going to get equality both of these equations. So they satisfy the equation. This is a special kind of system. Whenever the right-hand side, the constant terms are 0. Make sure here there's no constant term floating around. But if all the constant terms are 0, you have a linear system, then the 0 vector is always a solution. So homogeneous systems, which is what we call such systems, are always consistent. If the right-hand side is not just a bunch of constant 0 terms, then we would say that the system is inhomogeneous. Sometimes inhomogeneous systems are consistent, sometimes they're not consistent. We don't know. But homogeneous systems, they're always consistent because they have the trivial solution. If you have a system where all the coefficients on one side are 0, we'll say that the system is degenerate. I mean, you only need to have one equation where that's the case. So if all the coefficients end up being 0 for one equation in a system, then we say the system is degenerate. If on top of that B, the constant term, is different from 0, then you end up with something that looks like 0 is equal to something which is not 0, and that's impossible. That's an incompatible equation. The system is inconsistent. If on the other hand B is 0, if the right hand side, the constant term, is 0, then we have the equation 0 equals 0, which, while not super informative in terms of the content, doesn't really tell us what the solution would be. It is at least consistent. It is not a statement which is false. So if you have one equation, and only one equation, that looks like 0 is equal to 0, then every vector is a solution. If you have a linear system which contains a degenerate inhomogeneous equation, meaning to say that on the left you have a bunch of zeros and on the right you have something which is not 0, that's what inhomogeneous says, and degenerate means that everything is 0 on the left, then your system as a whole is inconsistent. And these are the only possibilities, really. Any linear system with real or complex coefficients, although we're not going to talk about complex numbers here, either has a unique solution or no solution or infinitely many solutions. And that's a remarkable result, because if you have nonlinear systems, that isn't true in general, right? The equation x cubed equals 0 only has one solution. X is equal to 0. X squared equals 64 has exactly two solutions, minus 8 and plus 8. And x minus 2 times x minus 1 times x plus 1 times x minus 2 is equal to 0. You could expand that if you wanted. It doesn't really matter. We've factored here. We've given it to you as though it was factored. There's only 4 solutions. 2, 1, minus 1, and minus 2. Sorry, here it should be a plus, not a minus. My apologies. Let's roll that. This system has exactly 4 solutions. But the point is that it doesn't have infinitely many. You can have more than one, but not like infinitely many. For linear systems, that's not the case. It is very convenient that linear systems only have 3 types. Systems with unique solutions, systems with no solution, and systems with infinitely many solutions. And that convenience, and eventually, as we'll see, the ease with which we can actually solve these problems, is part of the reason why people use linear systems all the time. But I do need to warn you, outside of the walls of this classroom, when you're trying to do, apply mathematics for real in the real workplace, the fact that linear systems are convenient doesn't mean that you should be using linear systems. It could very well be that a linear system is the poor choice to model the situation.